Hi, welcome to the JE Plugins channel, where we discuss audio signal processing and apply methods to generate audio effects plugins. In this episode, we will be discussing digital filters. The topic of digital filtering is vast, and we will barely be touching the surface with this episode. Mathematics and theory will be left for later episodes. However, by the end, you should have a basic overview of what they are and how to implement them. So, what are digital filters? Digital filters mathematically remove, attenuate or amplify frequency content in a digital signal. The most common filters are low-pass and high-pass filters. The former smooths out quick variations in signals, removing the high-frequency content. This essentially takes an adjustable moving average of a given signal. The latter removes low-frequency content from a signal. This can be seen as taking the moving average of a signal and subtracting that from the original signal. Other common filter topologies include notch, band pass, band stop, peaking, and shelving filters. Let's discuss some of the common terminology used when comparing digital filters. The frequency cutoff frequency or corner frequency is used to describe the frequency at which the filtering starts or is centered. However, the technical definition is the point at which the filter attenuates frequencies by 3 decibels or 6 decibels for Linkwitz-Riley filters. This is sometimes referred to as the half-power point. The filter order is used to describe the steepness of the filter, or how aggressively the filter attenuates across the frequency spectra. This is typically measured in decibels per octave, but is sometimes measured in decibels per decade. The quality factor and bandwidth are two metrics which describe the filter order. The higher the Q, the steeper the filter, while a filter with a large bandwidth will have a wide transition. Filter coefficients are what make a filter work and define the filter behavior. They are mathematical weightings that are applied to the relevant previous inputs and outputs to calculate the filter output. The frequency response, sometimes referred to as the magnitude response, is the effect the filter has on the output level across the frequency spectra. The phase response is the effect the filter has on the phase of each output frequency. This is often plotted on the same graph as the frequency response. Now, we will discuss some filter types. Finite impulse response or FIR filters are digital filters which output is calculated using only previous input samples. This topology is often referred to as feed-forward. Because of this, the impulse responses of FIR filters are finite and do not ring out forever. FIR filters are useful as they are easy to implement and can be designed to have a linear phase response, which is desirable for certain tools such as mastering equalizers and anti-aliasing filters. However, they can be computationally expensive when a particularly steep filter is required. This diagram shows an example filter structure of an FIR filter. Previous input samples are saved and multiplied by their relevant coefficient. Those samples are then summed to calculate the filter output. Infinite impulse response filters, or IIR filters, are filters which are calculated using both previous input and output samples. Output samples are fed back into the filter input. This results in an impulse response that technically rings out forever. IIR filters are commonly used as they can be designed to be very computationally efficient. They also typically require less filter coefficients for a filter with the same steepness as the equivalent FIR. A very basic IIR filter is the one-pole IIR, which is commonly referred to as an exponentially weighted moving average filter. This filter has just one coefficient, which is the previous output sample. This filter is commonly used for simple filtering tasks. The cutoff can also be calculated using a time constant as opposed to raw frequency, which makes it a useful filter type for smoothing control signals or applying timing to compression envelopes. The biquad is another IIR filter type. Due to its efficiency and flexibility, it is widely considered the Swiss Army knife of digital filters. The biquad has many applications and can be set up as any one of the filter types mentioned in the second slide. A single biquad is a second-order filter structure. However, filters of any order can be modeled as a cascade of biquad filters in series. This figure shows a direct form 1 biquad filter. The biquad can be set up in other forms which will be discussed in a later video. Now for some examples in MATLAB. If you do not have MATLAB, you can follow along using Octave. However, you may require additional packages for certain functionality. This MATLAB script will demonstrate various biquad filter types. MATLAB functions for different biquad types have been created based on the theory detailed in the Audio EQ cookbook. The Audio EQ Cookbook is a fantastic resource which details how biquad filters are implemented. You can find a link to it in the description. A function which plots the FFT of a signal on a semi-logarithmic axis has also been provided, which we will use to plot the frequency response of each filter. The main difference between each of the filters is the calculation of the coefficients. The shelving and peaking filters also require the calculation of a gain variable which is used in the calculation of their coefficients. In each filter we have state variables that store the previous two input and output samples. The difference equation used to calculate the output of the filter is identical for each filter type. To capture the frequency response of our filters, we need to take an impulse response of each filter. Therefore, we import a delta function, which is a signal where every value is 0 except for one non-zero sample point. We also normalize the delta function so that the non-zero sample point is equal to 1. Filtering our delta function with a low-pass filter allows us to plot the frequency response of the filter by running an FFT on the output impulse. In this example, we have used a frequency cutoff of 500 Hz, and we can see that the -3 decibel point, or the half power point, is at exactly 500 Hz. Doing the same with a high-pass filter reveals a similar story. However, the frequency response is inverted along the frequency axis. Note that the frequency cutoff still returns an attenuation of 3 decibels. Plotting our notch filter reveals a complete removal of frequencies around the cutoff. If we reduced our Q or increased our bandwidth, the size of the notch would widen, removing more frequency content. Our peaking filters require us to specify a gain value. We will use 6 decibels in this example. We can now see that the filter boosts frequencies by 6 decibels around the cutoff. If we specified a negative value for gain, this would have been an attenuation. The final example demonstrates shelving filters processed in series. We have also set separate cutoffs for the low and high shelf, which results in a toned stack-like frequency response. Similarly to the peaking filters, we can also attenuate. Finally, I will now demonstrate a C++ implementation of a biquad filter, which we will be using in the next episode in an audio plugin. In this implementation, we have defined an enum class with the different filter types. When used, this will return an int, which we can use to activate the correct case, which returns the filter coefficients for the relevant filter. In the class, we have declared functions to initialize the filter and change the parameters in real time. We also store our coefficients, previous samples and filter parameters as private variables. We have also defined the function which will calculate our filter based on the selected parameters. Moving on to our CPP file, we have our definitions for our initialize and set parameter functions. The latter functions will only recalculate the filter coefficients if a parameter has been changed, reducing the required calculations. Our reset function resets the previous sample values to 0, and recalculates the filter coefficients if the sample rate is changed. Our process sample function calculates the filter output for the current sample and saves the previous samples for the next calculation. This concludes this episode on digital filters. Stay tuned for episode 3, where we will be using the topics discussed in the last 2 episodes to implement a tube screamer effect in Juice. Bye for now.